This is video 21 in the thermal course with Lars Erik. It is about development this equation based on a flash situation. The flash situation is that we have a feed with a known composition. The sets are the fractions, F is the total feed. Then we have a flash with a pressure and a temperature, and we have a vapor with a vapor composition with the Y's, and we have a liquid with the liquid composition, the X's. And we assume that it is equilibrium between the vapor phase and the liquid phase. And then we start with material balances. The feed equals L plus V. We assume that it is steady state. This can be written that 1 equals L over F plus V over F. And then we have a component material balance. This equation states that the amount of component I in the feed equals the fraction of component I in the liquid times the liquid flow plus the fraction of the vapor of component I times the amount in the vapor flow. Then set I equals xi times L over F plus y times V over F. I just divide it by F, and set I is yi over k. Ki is yi over xi. That is what is meant by k. And I just manipulate this equation. And we get a revised expression for the set. And then the reason why we did this manipulation is that now set is expressed by the y, and else there are the k values and the V over F ratio. And then the y can be expressed by z over 1 over k plus 1 minus 1 over k I V over F, or y I equals to z I times k I divided by 1 plus k I minus 1 times V over F ratio, and this is equation 1016, and we have a similar equation for the x's. K is y over x, so we easily convert this to an equation for the x's. For some reason in the textbook they have developed this first equation for the y's in chapter 10, and then we add one more equation here in chapter 14 when we are calculating the different conditions, but this is the equation 14. 16, and then we go further, and then I put up a question: why using a function which is the sum of y's minus the sum of x's equal to 0 as an iteration variable. The topic is that we use this function, the sum of y's and the sum of x's equal to 0, as an iteration variable. We can refer to figure 14.5 in the textbook. We can make an fy expression which is the sum of all i's of zi ki divided by 1 plus v over f times ki minus 1 minus 1. This is the sum of all the y's minus 1. That should be 0. And similarly, we can put up an equation for the sum of all the x's, which in this case is expressed by 16. And since that sum should be 1, we can subtract 1 and say that that should be equal to 0. Or we do not need to state that either. We can just say that Fy is this sum minus 1 and Fx is that sum minus 1. And a general solution procedure is that F is Fy minus Fx, or the sum of sets I, Ki minus 1 over 1 plus V over F, Ki minus 1. Should be equal to 0. This is 1490. And this is the Rashford-Rice equation. From 1952. And this is efficient because dF over d over v over f is always negative. Or f of v over f is a monotonic function. That is, if we change the vapor to feed ratio, then we know that this function is a monotonic function, so that we will always get a solution to this. We can vary this, and we can be sure that we will get a solution to this. And what is perhaps more important than efficient is that it is robust, which means that we will always get a solution. And the procedure guess V over F, and calculate F, if f is 0, then calculate the vapor, liquid, the whites, and the excess. Else, try a new V over F. That is a efficient and robust calculation procedure to calculate a PT flash. Then one more comment is that in modern process simulation tools like Aspen HYSYS, more efficient algorithms using extra variables are used, and one example is this inside out algorithms. So here first we have developed working equations for the liquid fractions and the vapor fractions, and then it is shown that these can be used in a method for calculating a function based on the vapor to feed ratio that is monotonic, that is, it is easy to solve, and then that is a reasonable basis for a procedure by guessing and iterating on the vapor to feed ratio, and this can be used in algorithms, but in modern process simulations programs like Aspen HYSYS, they have even more efficient algorithms, adding extra variables for iteration. But this is meant to give an idea of how this can be calculated in a computer. So this ends video 21.